Though quantum mechanics in the end replaces our classical understanding as the more fundamental theory of how we look at the world, of course there are many important ideas and models from classical physics that remain really very useful. You don't have to throw away everything you already know. In fact, if we did, doing that would make our job much harder here. Many of the intellectual approaches we constructed as we developed our classical view of the world round about us turn out to be very useful as we develop quantum mechanics. We can reuse these. Sometimes we repurpose them. We use them for something else we didn't use them for before. But many of these concepts remain very useful as we build our quantum mechanics. For example, in particular, our understanding of waves and oscillations is very important. It's also true that our quantum mechanical view of the world has to correspond with the classical one. In other words, we have to be able to explain what classical physics can already explain. So, not surprisingly, many concepts from the classical world remain valid in quantum mechanics. In particular, for example, ideas like energy and momentum. Part of the process of learning quantum mechanics is really understanding what concepts we can keep and what ones we simply have to throw away. Here we're going to remind ourselves of some of the basics of classical physics, both to set the ground for what is different about quantum mechanics and to set up some concepts that we're going to reuse later, as I said, sometimes in new ways. We're going to start by reminding ourselves of some very basic ideas from classical mechanics, such as the idea of kinetic energy, momentum, Newton's second law, potential energy, force. Once we've done that, we'll look at simple oscillators, such as the mass on a spring, something that bounces up and down on a spring, and how we describe that mathematically. Finally, once we've done that, we'll look at waves, including ideas like standing waves and diffraction. And this will all set us up very well to start quantum mechanics proper. Compared to the amount of mathematics we need for quantum mechanics, perhaps somewhat surprisingly, there is not so much physics we need to know. We do need to understand these basic ideas I already mentioned, the ordinary classical mechanics of Newton's laws. The ideas of relativity, which of course are beyond Newton's laws, are essential for the advanced physics of elementary particles, and that's a very important and exciting area of science. However, for the basic ideas of quantum mechanics, and for nearly all the applications we find in current engineering, we do not need to introduce relativity. This also means we can come to understand the core ideas of quantum mechanics without the additional conceptual difficulties of a relativistic view of the world. So, to prepare for quantum mechanics, let's review some of these important ideas from classical physics.